marker horizon, scrounging and trying to get that back. The second point I want to make out is that my title is slightly different than the one that was sent out, with the point being that I'm not going to talk so much about the future. I'm more talking about what's happened in the past and how that might help us think about the future. And so as I get started, I want to also make a clarification that when I'm talking about coastal wetlands in Apalachicola area, I've got the opportunity to include everything from barrier islands, salty coastal wetlands, all the way up to the tidal freshwater reaches of the delta. So we're going to have several different vegetation types that we're going to be talking about today. And before I move any farther, I want to make sure I acknowledge people who are very big contributors to this. So I've got a graduate student, Simone Schuster, who is doing some coring work, and I'm going to show a little bit of her preliminary data. And then I just can't overemphasize the contribution. This data set is collected and managed by ANER, and there's just a mass at the Apalachicola NER. There is a massive effort that happens every spring and every fall to go collect all this data. So I've listed a few of the staff members that have been a part of this, including people that are helping already this year, Meredith O'Donnell, who's their new set coordinator. But just really, like, they're doing a ton of the work here, and I'm just sort of the voice presenting some of this and integrating some of it. So if my slides will advance. There we go. All right, so welcome to North Florida. If you're not familiar with the layout where I'm at, so this is the state of Florida. This white box is where I'm at up in the north. So the Apalachicola River is fed by headwaters coming out of the Appalachian Mountains. It's got the Flint and the Chattahoochee rivers that flow down through Georgia and Alabama before where they meet at the Florida border. You've got then 107 miles of the Apalachicola River that flows through basically 144,000 acres of pretty pristine floodlands, tidal floodlands, or not tidal, but the floodplain in the river. And as that comes down then to the coast, it comes down through, meets Apalachicola Bay in the center here, and they've got St. Vincent Lagoon out to the west, and then St. George Sound over here to the east. And just to show you sort of like an orientation of where people are at, I'm talking to you from the FSU Coastal and Marine Lab up here. And main campus for FSU is basically if you go an hour straight north of here. And then right down next to the bay is where the Apalachicola NER offices are at. And I'm going to be talking to you about wetlands that sort of ring this whole area around where the NER is at. I want to start with some basics. I figure we're all wetland people, so this is not a lot of new material, but I want to sort of set a context so we're coming at this from the same perspective. So wetlands and sea level do interact with one another dynamically, and that includes both an ability to move laterally in response to sea level change and to move vertically. And so being a talk about SETs and marker horizons and lead 210 dated cores, most of what I'm going to talk about is vertical change that has to do with both these processes that are additive and subtractive to the material that's there, the mass and the volume that's in the ground. But if you hold with me long enough, by the end of the talk, I'm going to come back to some things related to lateral movement as well, in terms of how we're interpreting some of our data. Right. So I want to start with referencing a couple of papers that have been informative for just getting me thinking about this question about the most recent decade. So this is a paper that came out in 2023 by Dongendorf et al. And there's this quote they have: "We report a mean sea level acceleration in tide gauge records along the U.S. Southeast and Gulf Coast that has led to rates greater than 10 millimeters a year since 2010 that are unprecedented in at least 120 years. And so what they've done is they've collected a bunch of data, and one of the important points here is that this is focused on the Southeast. It's not a global signal, right? It's a regional signal they're picking up. So this is just an example. They use the Pensacola tide gauge. You can see the yellow line is the nonlinear trend moving through the tide gauge record. Then down below here, they show what the rate is in millimeters a year, and that's the yellow line. So you can see in some cases it's going up, in some cases it's going down. And so that's approximately a 100-year record there showing periods where when it's increasing and decreasing. But in the bottom, they're showing the probability that at that period of time, there is an acceleration occurring. And so you can see that there's been periods in the past, 1930s and up to the 50s, maybe in the early 1970s. And then you can see this big block of red coming towards the present, and particularly around 2005, 2010, it crosses this line of 100% probability that what's happening in this tide gauge record represents an acceleration. And then what's neat is they take data from tide gauges all around. You can see this from basically from Texas all the way around up to the northeastern US. And the color here represents the acceleration coefficient. So this has nothing to do with what the actual rate of sea level rise is. It's the acceleration from year to year. So this is millimeters per year. And what you want to notice is that the dark colors represent an acceleration, and the lighter colors, as you move further up into the northeast, get lighter in color. So there's less of that pronounced acceleration. And so what they're saying is in this southeastern region, we have an acceleration bringing rates up to greater than 10 millimeters a year since 2010. And there's another paper that came out actually the year before that, and this is led by Randy Parkinson down at FIU with Shimon Wodanski, who's at University of Miami. And they're saying in their paper that analysis of 4 South Florida tide gauges with records ranging from 27 to 116 years indicate the average rate of sea level rise has accelerated from 3.9 millimeters a year if you take the long time frame from 1900 to 2021, to 6.5 millimeters a year if you look at the window from 2000 to 2021, then all the way up to 9.4 millimeters a year over the past decade. And Randy has this question towards the end of the paper when he's talking about sort of implications of things that they find. And he says, so several knowledge gaps are identified. And I want to jump to this point here where we get to the bolded text. And so what he's suggesting we need to do is we need more information about recent sediment accumulation to determine how, in their cases, how South Florida coastal wetlands have responded to a sustained acceleration in the rate of sea level rise over the last decade. So what I'm basically doing is taking that directive from them and pulling it in, making that the point of my talk, which is to say, have North Florida coastal wetlands responded to that sustained acceleration in the rate of sea level rise over the last decade? So I'm going to approach this question in the Apalachicola Bay area using the sets that ANR established back in 2011 and 2012. And so they actually have a few more stations, but I'm just going to focus on these. There's 3 different sites. There's 2 stations at each of these sites in the river delta, in the bay side, and then out on the barrier islands. And another thing, and so the vegetation types change here as well. So up in the riverine distributaries, primarily you have sort of sawgrass marsh sets that are the first ones you run into that are right off the rivers. And then the further inland you go, it transitions more to forest, including things like bald cypress. And then East Point is almost exclusively Juncus ramarianus, the black needle rush. And then as you move out to the barrier islands, it's a little bit of a mix with, it's mostly Juncus, but there's some Spartina. And then there's also at a couple of sites, there are red and black mangroves that are showing up. And so the mangroves are going to be a little bit of part of the story that I tell at the end of this as well. And then all of these surround where the location of the Apalachicola tide gauge is located. And then the last thing before I move on is not only is the vegetation different, but the soil is very, very different as well. So up in the distributaries, that soil on average has 53% organic matter in it. So you move over to the bayside sites, that's about an average of 44% organic matter, and then a massive drop when you get out to the barrier islands where it's much more sandy and mineral rich. And so on average, right, this is using soil cores that are about 30 to 40 centimeters deep. On average, your SOM is much lower, about 6%. Okay, again, most of this group, I think, very familiar with the tools that we're going to talk about, but I just want to make some points to make sure we're sort of talking on the same page. So there's different tools. They operate over slightly different, somewhat different timescales, and they sort of cover different depths within the wetland soil profile. So first of all, we have tide gauges, and I'm going to talk about that a little bit more, but that's, you know, pulling from data like the Dongendorf paper and like the Parkinson paper. So this is getting what the water level is doing. Then we have a bunch of sets that I've already talked about, but one of the things I wanted to point out that's neat is because this is a river delta, there's a lot of unconsolidated sediment. So the rods on these R sets are anywhere from 20 to 24.5 meters deep before they reach some sort of, you know, consolidated sediment or bedrock where they're not going any further. And again, the set is representing what we're measuring with that deep rod set is the overall change throughout that whole profile. And then the third is I'm going to talk about marker horizons. And the distinction I want to make here is that we're talking specifically about surface accretion. And this is slightly different from the fourth tool, which is the deeper cores that are 40 to 50 centimeters deep in general, that are dated with lead and cesium. And the idea being we report both of these as accretion, but which is basically depth divided by time. But for the feldspar, you're basically looking at deposition, what's coming in at the surface, and the lead-210 core is going to often include root ingrowth and decomposition and things like that. So there's kind of a hybrid thing going on with the deeper cores that's like a mix of the marker horizons and the set records to some extent. And one of the things that's neat about all these is that they report things in units of depth and time. So mostly I'm going to talk about millimeters a year, sometimes centimeters. And one of the neat things we can also do with lead-210 is we can get mass accumulation rates. So that'll be reported in grams per meter square per year. Okay, so we're going to start talking about the sea level record now for Apalachicola. So this runs from 1967 all the way up to the present. And what I've done for today's talk is I've excluded any data from 2026. So this just runs up through December 2025. And if you'll notice, I've plotted just the linear trend, a simple linear trend through the entire record. And the record over that whole time, that slope is 3.13 millimeters a year. You may also notice off to the side here, I've got a number 2 pencil. And the reason for that is if you take the average of the depth for the first 5 years, 1967 to 72, and then the last 5 years, 20 to 2025, that difference in elevation, or that total amount of change, is 19.2 millimeters and 19.2 centimeters. And a number 2 pencil turns out to be 19 centimeters long. So for a record, if you're just looking for a visual gauge, that's the amount of change that's happened. I'm a big fan of using visual guides because sometimes I have a hard time figuring out exactly how much change we're thinking about. So if you can hold a pencil up, that's the amount of change that you've had happen in this amount of time. Now, with that said, there's obviously lots of different ways you can look at this. If we take just the period 1990 to 2010, so this precedes the Dongendorf and the Parkinson comments about the acceleration sort of starting in 2010, you'll see that this is actually a period of relative quiet. So this is only 1.1 millimeters a year over that 20-year period of time. But then when you look at that period of time that Dongendorf and Parkinson are talking about, you can see the rate is really substantially elevated in Apalachicola. So it's 12.42 millimeters a year for that period of time. So let's jump into the data. So the way I'm gonna do this is I'm gonna start up here with the riverine sites, and then we'll just move around the bay down to the bay side and then out to the barrier islands. So this is the record from 2012 to 2025. These are the marker horizon data. So this is the depth to feldspar divided by the time since that feldspar was deployed. And what you can see is, if you look at the y-axis, this is the rate in millimeters per year. So in terms of accretion, these are pretty healthy numbers. You might even argue that they're pretty extreme numbers, but it's indicative of a river delta that's moving a lot of sediment, or a relatively large amount of sediment. This is by no means a big river in terms of global scale, but it is moving sediment. If you look at the sets, then their record over time, and what I'm doing here is just fitting a linear slope to the total record. And I'll show you more of these details in a little bit. But you're seeing, again, pretty healthy elevation change. And then what gets kind of interesting, you start to then compare, well, what does accretion look like versus elevation? Because is the elevation change coming from the material that's being supplied at the surface, or is there subsurface change that's contributing to that? And what I've done is just sort of used a color scheme. So green means there's a one-to-one relationship. So at one of our sites, or sorry, one of the stations, there's a one-to-one relationship. So accretion and elevation change look like basically the same thing. You go to the other site, these are over on the East River. This is between 1.5 to 2 times, where marker horizon data basically is double what you're getting from the reading from the sets. And then 3 of the sites are considerably higher than that, 2.5 to 3 times greater for the marker horizon accretion than the elevation change. So then the question becomes, well, what happens when we compare that to the sea level rates? And so if we're just doing rate comparisons, both the accretion data and the elevation change data look great compared to that long-term average of 3.1 millimeters a year. That's the full complete record from the Apalachicola tide gauge. You might argue then, though, once we start to look at that acceleration, that it looks like some of the accretion numbers are doing okay, but overall elevation really lagged. And so you might be tempted to make the case that there's a very strong deficit in terms of rates. But what I want to make a suggestion is that the rate comparisons aren't as important so much as the elevation comparisons. And so these then are the records versus mean sea level. So the mean sea level record is plotted in blue, and both of these, then the black data is the means for each time point for each of the SET stations. And these are referenced to the same data, so the NAVD 88. And on average, for all the river sites, they are 37.4 plus or minus 2.9 centimeters above that mean sea level line. So even though there's a lag in some of those rates, there's no indication in the riverine sites that there's been any kind of massive change or alteration in trajectory that indicates something has changed for the worse. What I want to do then is for each of these, I'm just going to highlight a couple of them because I don't have time to go into all of them. But what I'll do is I'll highlight first the Little St. Mark's, the marsh at that site, because this one had the greatest amount of elevation change, and the St. Mark's Forest, where there was the least amount of change. And this is what they look like. And I've tried to do this so that the scales are proportional, right? So this one at Little St. Mark's, that marsh elevation change is about double what we saw happen at the St. Mark's Forest. And what I want to do, this is maybe kind of gimmicky, but again, for like a visual reference to be able to think, well, what does this actually mean? You know, what do millimeters mean? And so here are 2 objects that you can use that maybe help you get a sense of what that elevation change in this relatively brief period of time actually looks like. So the Little St. Mark's Marsh is a little over 129 millimeters, which is about what the width of a standard dive mask is. And then this is a standard MLB baseball, which is 73 millimeters. And so this record is 70 millimeters between the minimum observation and the highest observation of elevation. So this is basically what the net overall change has been in elevation for each of these sites, for each of these stations. Pair this now with some of the lead 210 data. So this is a work in progress, and I mentioned that this is sort of inconclusive at this point because we have more work to do, and we only have 2 of the 6 cores dated so far. But they sort of give different stories from the 2 different cores that we've got dated so far. And just to sort of lay out what you're looking at, on the left-hand side is the average accretion rate. So that's in millimeters a year, and that's in these open circles. And you'll notice that accretion on this for the Little St. Mark's River Marsh site is slowly decreasing. And for the St. Mark's River Forest, you actually have a very strong signal of increasing accretion rates over these time scales. So these are averaged over the 100 years, 50-year, 25, and 10-year time scales. That doesn't mean that's the rate 100 years ago. It's that rate averaged over the full 100 years. And then the black dark circles represent the average mass accumulation rate. And this is in grams per meter square per year. And you can see that the marsh is sort of It sort of was decreasing, but then there's a little bit of an indication of an increase in mass accumulation at the end. Whereas again, the forest basically shows a strong increase in mass accumulation throughout the entire record. So this is, a work in progress. We move around then to the bayside sites, and I've tried to keep the scales the same. So if you remember the first one, that some of the numbers were a little higher. These are the accretion rates that are seen in this area, and this is not as surprising because there's not, so much riverine influence. And so these accretion rates are a little bit lower, but still strong, up around anywhere from 6 to 8 millimeters a year, with the exception of the East Bay site. The East Bay South site. And you look at the elevations; they're pretty, the elevation change, and they're pretty similar. And so what's interesting about this site is there's a little bit more agreement between them. So 2 sites are basically a 1-to-1 relationship. 3 of them have like a 1.5, where accretion is about 1.5 times what elevation changes, and then the one station at East Bay South, where accretion is about 3.5 times what the actual elevation gains are. And a similar story to last time, they all look pretty good against that 3.1 millimeter average, but in this case, both accretion and elevation are pretty strongly lagging whatever that accelerated sea level rate was. And so again, you might be tempted to say that there's a pretty strong rate deficit, which indeed there is. But again, there's a really strong elevation comparison between them, so that you see pretty strong, long, linear, steady relationships with a few aberrations over time. But these sites in general, these set stations, are about 27.6 plus or minus 2.5 centimeters above that mean sea level record down below them. And here I'm going to talk in just a little bit more detail again about East Bay North 2 and East Bay South 2. And what you see basically is that this one, East Bay North 2, is about twice the elevation gain that we saw at South 2. And if I go back to the imagery, so the greatest amount of gain we see in East Bay is the same as the smallest amount of gain we saw in the riverine sites with the baseball. And then the least amount of gain we see in East Bay is about the size of a AA battery, and that's about 50 millimeters long. But just to finish up, basically, I don't see a strong sign of a deterioration here in response to that most recent 10-year acceleration. I'm going to follow up on that in a little bit, though. Okay, so now we move out to the barrier islands, and this is where things are going to get a little bit more exciting, because we do see some more changes going on. I do make a note up top here. So this record is from 2013 to 2025, whereas all the East Bay and the riverine sites are from 2012. So there's one less year of data on the barrier islands. And you can see, looking at the marker horizon data, the vertical accretion is substantial. We're getting up over, in some cases, when you're talking 20 millimeters a year, you're talking 2 centimeters. So it's a lot of accretion happening at the surface. Keep in mind, these are the linear trends, though. You see 2 of the sites that are also missing marker horizon data, and I'll explain that here in a second. So when you look at the set data, this scale has had to be adjusted, but you see a couple of them with really strong elevation gains, one kind of average that matched that long-term sea level rise record, and then 3 of the sites that are actually, 3 of the stations that are actually losing elevation. And if you can do that sort of the ratio again, 2 of the sites have a pretty good 1-to-1 relationship where the amount of accretion is what's happening with elevation change, and then 2 of them are showing either way more accretion than you're seeing in elevation gain, or a strong elevation loss. And I'm going to jump then to these long-term records, which, so, if you take just 4 of them, so that top row and then this one over here on the right, those 4 stations are looking okay, right? They have the highest delta between, or the difference between what their mean elevation is and that of mean sea level of 43.1 centimeters. There are several of the sites, though, that something different is happening. And so what I'm going to do for this one, for the barrier island sites, is I'm going to talk about all three of these and how there's a similar story happening with these two, and then something with Unit 4 that's perhaps a precursor to what happened at the other two sites. So this case is kind of fun, because if you look at, this is the first place where we've seen a declining trend at any one of the stations. And then we have this other one where there's just this enormous increase. And I've actually had to, this would blow out scale I've had on the other slides as well. This would be 3 monitors tall. So much bigger increase. And so you put these together, and this decline at the Pilot's Cove Marsh has been as much as some of the smaller gains at the other sites. And then obviously at the Unit 4 place, we've got a massive basketball scale. I mean, so if there was a basketball sitting out there in 2012, it's now buried by the time you get to the present day. And I'm going to show you some pictures about that here in a second. Okay, so what I want to start with first is Nick's Hole. And if you look with me at the top row, this is in 2013. The 2 green boxes represent the 2 stations that are located at that site. And the red line represents where we interpreted the shoreline where the water and vegetation met at that time. By the time you get to 2019, you can see that that's actually moved considerably, so that the seaward most station is completely in the water. And if you look in the present day, indeed, that station is completely in the water. So there's the collar in the middle of the set station, and it's fully underwater. Vegetation is still there though, right? It's not like it's just totally transitioned to an open water site. There are times when it's low tide that there's still vegetation present there. So it's been interesting to have conversations with the ANER staff, but these stations like this are still being measured. And what's neat, if you go and look at the actual record, then you can sort of see that in the early couple of years, 2, 3, 4 years, it was above water. And then you hit this point where in the written record that goes with the set observations, you first see the word underwater showing up right here in 2016. And so what I've shown over here on the right is these are the notes from those set measurements over time. So you'll see first on April 14th in 2016, the elevation rod is not stable, lots of accumulation of sediment inside, 1 foot of water over the set. Then in October of that year, just the observation, set is underwater. April of the next year, wet with standing water. And then again, so you just, as you read down, you keep seeing more and more. This is every year, completely underwater, very high tide, low tide, partially underwater, et cetera, et cetera. So it's, interesting to see that story sort of mirroring see the data walking in lockstep with what the observations are. Then we move to the PC1 marsh. And this is similar, but the timing's a little bit different. And here you can see pictures of Sam and Stephanie I think this is last fall, out measuring, you're in water. They're wearing waders, not just because they want to keep their feet dry, but because it's, waist deep water all around. And so this is that picture as well, right? You can see the collar underwater. So on July 14th of 2020, entirely underwater, made it nearly impossible to obtain cores. October of 2020, cores need to be done at low tide. 2021, station underwater, and it was abandoned. That was the talk of abandoning it. We actually went back and continued in October. And so there's challenges that come with this in terms of what do you do with a set once it's underwater? Because in this case, they're talking about the PVC tube is filled with mud and mussels. The collar had flipped up. Seagrass is so thick that it was hard to tell if pins are on the sediment or on the grass. The set is underwater. And that just keeps going, right? But what's interesting is you can even go down to like from April of last year. So the plot was not inundated, but it was wet. So, water doesn't stay level. And there are times when the sites are still on that low end of the intertidal frame. And then I want to show you, so if you see that red arrow, this is looking landward towards where the second station is located, and it's just behind this berm where there's a bunch of salt bush growing along the high elevation sand dune that's there. And so if you get around to the back, this is Ethan Burke, who's setting up the pins to make the measurement. So if you look forward from him out to water, that's where the other set station is at, that is now basically an open ocean set. And what I want to show you, this is the day I wasn't actually there, but there was a pin obstruction in this set. And if you can see the guy in the water there, you have to be a little more careful with these guys than you do with moving crabs or snails or things like that. All right, and then this is slightly different, but again, I think it's something fairly similar happening. So this is imagery on the top left from 2020, early 2021, and you can see sandy, there's a little bit of a berm here, and then here's the two set stations. And if you look around, so here's two people standing, and then there's mangroves that are in here. And at this station, they're all red mangroves. And what you see that's a little bit different with this one is it wasn't water that was coming in, it was a heavy sand deposit. So as time is going on, it's a very linear relation, very just flat and stable. And then you see this bump up, and the picture down the bottom left shows that sand dune has now encroached into the set footprint. And so the same thing, if you look at the notes, it's really cool to just see in 2022, north and west quadrants both have heavy sand deposit. They noticed it was about 36.5 centimeters, had to use a tape measure. Then it gets to other notes. They're like, the collar's in place and stable, but we have to switch to the tan pins. These are the shorter pins due to the dune accreting into the set. We need to get a longer ruler. Due to the dune moving into the set, we need to use these different pins. We got to discuss what we're going to do with that moving forward, etc. So show you one more set of pictures. So this is in April 2021. And that's the station that you can see nice and clear. From this picture alone, you wouldn't know that there's some problems coming down the road. And these tubs, basically, we cut the bottom out of it, and then using a flour sifter, that's where you apply the feldspar for the marker horizons. And so the bottom picture shows the two new marker horizons that were deployed. And then this is just from February of this year. And note the red rectangles. So those are the markers on either side of that station, and the dune now fully occupies that set station. So the collar is buried, the feldspar is very, very buried, the boards are buried. It's well under the sediment. I want to take this opportunity to also start talking a little bit about the mangroves. So first of all, notice in the picture on your left, there's a nice healthy red mangrove. This one was burned and died out in the 2022 freeze that we had. And it was basically right around Christmas, something like the 24th or 25th of December. And so that one is a legacy of that freeze event. Then all these little brown ones, the brown leafed ones that you see around, that actually was a freeze event we had in January of this year. So those guys were affected by that. But the thing I think that's really interesting, look at the green arrow. So look at your picture on the left and look for those mangroves. They're not there. So between 2021 and 26, so 4 years, a big group of fairly mature mangroves have moved in, and they're fairly big at this point, and they're not damaged. So those are right down next to the water line on the back side there, and there was very little leaf damage on those. So these freeze events are setting some of the mangroves back, but they're growing quickly, and they're propagating and dispersing very quickly. So I think mangroves are here to stay. So I want to get back to the lead 210 then. One of the things you might be thinking is, okay, I'm comparing rates of change with a sea level rise so going back to a period of time where sea level rise started to accelerate at the same time these set stations were installed. So how do I know if the set stations are responding to anything or not? And the truth is we don't, right? It's just a question of whether or not the sets are looking stable, or if there's anything unhealthy about them, like we've seen in some of the ones on the barrier islands. The lead 210 lets us look back at a record from before that, so we can start to get an idea about whether accretion rates in the last decade look any different from accretion rates earlier than that. And so again, keep in mind, we're looking at the open circles, and for the black, these are 4 cores that were dated down at Pilot's Cove, so not too far away from where that picture with the little alligator was at. They're dated from specific vegetation communities. You can I'm not going to talk about the smooth cordgrass, the Spartina core, because that was an edge core, and I don't think it's very representative of that vegetation type. But in the black mangroves, the juncus, and the red mangrove, in all of those, you see from a mass accumulation standpoint, and in some cases with an accretion standpoint, the most recent 10-year average shows a dip compared to what the historic rates had been. So either they're going up, and then they're sort of tipping down. So there's an indication here that there has been some sort of a potential slowdown in sedimentation rates on the barrier islands in the lead 210 record. For reference, I just want you to look at these though too. So these are the two cores from up in the riverine wetlands that I'd showed earlier. Look at the mass accumulation rates. If you look at the right-hand y-axis here, you're looking at mass accumulation rates that are maybe 400 grams per meter square per year. But just to show you how different these wetlands are, if you go out to the barrier islands and you look at these scales for mass accumulation rate, up around anywhere from 2,000 to 3,000 grams per meter square per year. So very different very different sedimentation types. And one of the things I would think that it's kind of neat about this is it just is another thing that indicates that there's not necessarily a conservative relationship between the mass of sediment and the volume of the soil profile because of all sorts of different things, including compaction and sediment type and things like that. And then just to come back a little bit to the mangrove story, one of the things that's interesting, if you go back to 2007 and look at this place, this is in Pilot's Cove, the little orange circles, if you can see them, are where you get the indication of where some mangroves were present, even back in 2007. And then this image below it is looking at the same area, but it's looking at it from the side. And so this circle up here where there's a kind of a good patch of mangroves, that's this one right out here. There's a bunch of black mangroves that today are about 12 to 15 feet tall. So they've done very well. But one of the things that's kind of interesting to think about the mangrove story is whether or not this is just a temperature story or because it's sort of coincident with that acceleration in sea level rise, if that hasn't also contributed to helping to distribute the propagules into parts of the areas where they wouldn't more quickly than if sea level rise had been just a lot flatter and slower. Because on that picture on the bottom, if you walk transects across that site, which I've done several times, and it's a delight, there are mangroves all over in the Juncus. Like even the big ones you see don't give you an appreciation for just the thousands and thousands of seedlings that are all over out there. So this is definitely a place that's in transition. And these are pictures then on the right from another place called Dog Island. And the plot on the bottom is from a dissertation from Jen Bueno, who just graduated FSU in December. And this is showing the acreage of increase at these two sites as perceived by the unoccupied aerial vehicle. So it's basically what can a drone pick up in terms of mangrove area. And so it's a pretty dramatic increase that's going on. And that's going to have implications for sedimentation rates and things as well. And so just to wrap things up, go back to Dongendorf, to that paper I started with earlier. One of the things they state is that the recent sea level rise acceleration is not expected to continue. So they say, we demonstrate that most of the internal variability in coastal mean sea level is coherent with open ocean wind stress forcing through westward propagating Rossby waves in the tropical North Atlantic. In other words, it's not a global signal, it's a regional signal. And then they continue with the idea that it's likely that rates along the US Southeast and Gulf Coast will return to the average rates projected by climate models, they say within the next decade or so. And so I'll just conclude with this slide, which basically shows that even if you then look at our most recent 5-year record instead of the long-term or the most recent 10-year period, there's actually a deceleration. Again, this is just a linear, so it's sort of oversimplifying what's happening. But just to show that things have slowed down a little bit and maybe even are reversing in this area at this point. So just to reiterate, I think what's neat is the opportunity to look at that past decade as sort of a test case or like maybe test fire of what happens when rates do accelerate, how quickly do the wetlands respond, and are there deleterious consequences that accompany with it. And so with that, I think I'm maybe a little over on time, but thanks for being here and for attending, and I'd be happy to take questions if anybody has any.
Wow, thank you so much, Josh. That was really interesting, and I think a lot of us loved the scaling images that you included. It really puts it in perspective in a little bit of an easier way when you're just glancing at these. So yeah, I would love to open it now to have a kind of a joint discussion with everyone. You can either unmute or you can throw your question in the chat. I can go ahead and start off. How do you think that the SET networks could better capture responses to rapid changes in sea level rise?
That's an interesting question. So I guess my first thought is, well, we could make more measurements, right? We just like have higher temporal resolution to see if they're responding. Because one of the things I didn't talk about at all is what's the timing connection between when sea level rises and when the wetland actually starts to respond. And there's lots of questions. There's a lot more that needs to be dug into with this data set. But to just say that we should measure more often to pick up those signals, I'm not sure is feasible, and I'm not sure if it's useful. I think that's one of the things that maybe we need to poke at a little bit more with the sets and figure out how quickly the data respond to changes in sea level, or how much sea level change do you have to see, or water level in general, not necessarily just the mean sea level, to see how quickly or slowly things respond. And then, yeah, that last part actually that I was just saying, I think it probably depends what water surface monitoring spatial scale you're using. So in this case, all my comparisons are with the tide gauge that's located in Apalachicola. So there's greater distance, and there's all sorts of different factors affecting what sea level is, what the mean regional sea level is versus what the actual water levels at the sites are. And so that's a conversation that I've started with the water level monitoring group with the NER, because they have lots of places that are much closer that we could look at. It's not the same length of a record, but it's pretty much concurrent with the sets, and so we could start to do some more things with that. So more time, more work, but I think that'll be interesting and fruitful.
Definitely. Do we have any other questions, comments?
Oh, that's cool, Will. I'm curious how big your gator was. That guy was little enough it wasn't too concerning, but. All right, that's a little bit bigger. You got to watch out.
All right. If we don't have any other questions, do you have anything else you want to add, Josh?
Well, I guess one of the things to talk about is, there's talk and prediction about the potentially severe El Nino this year, and so we are in a pretty severe state of drought here right now, as I imagine much of the rest of the Southeast is. And so that's going to be interesting to look at, like maybe that will actually bear out with more of a response in the riverine wetlands compared to the barrier islands, with the freshwater inputs.
It'll be interesting to see how it plays out this year.
Yeah. And then I guess one other thing I can mention is that I don't think we've started tangling with yet, but several, especially the riverine sites, are prescribed. They're burned on a fairly regular basis I think it's 3-4 years, and so that's something that we're kind of interested in looking at in terms of what that's doing, because it's basically driving these big productivity boosts once you burn it and then allow that to come back. But the soil densities are really interesting. So just in terms of the surface is pretty stable, but the dry bulk density of these riverine sites, as shown in this picture, are really, really low. When you try to take cores in this site, it's almost impossible to do so without 50% compaction or more. It's really lots and lots of void spaces. And I'm curious to what extent that's just a normal condition in these types of vegetation, or if it's some sort of a response to fire as well.
Yeah. Lots to look forward to in upcoming years, for sure. All
And
right.
sorry, I'll add one more point. It's just like,
Go ahead.
please support your local like set monitoring effort, right? It's just that the data, it's a lot of work, but it's really, really useful. And the longer these data sets get, the more important that is. So keep supporting your set people.
Well, with that, we do have a couple announcements for SECOORA. We are happy to finally announce that the registration has officially opened for the 2026 SET Community of Practice Workshop from July 16th to 17th in South Carolina. I believe we're going to have registration available specifically to you all until April 30th. And after that, I think we're opening it up out to the public. So be sure to reserve your spot before then. The registration link I just dropped in the chat, but you can also find it on our website, and you hopefully should have also received an email a few days ago regarding that. Additionally, we are planning a new initiative to help expand our outreach to undergraduate and graduate students conducting work that's related to SCTs. And we would love your support to connect us with any current students or recent graduate students you know who has been involved with any related type of work. The hope is that we can allow them to form new connections within our organization, but it also allows us to broaden our network and accelerate the momentum in wetlands advocacy, as well as engagement. So keep an eye out on your emails, because we will send another one out shortly to hopefully get some more involvement. And as always, just feel free to reach out to us here with any questions or concerns about anything. And we just wanted to, from all of us here,